Welcome back to section 5 of chapter 12. This is the very last section that we will be covering this year. So, let's make it worth it. This one is going to be on mathematical induction, which is something we use. It's a type of proof, and infinite geometric series. So that's something we've been working with. Series, we're adding a whole bunch of stuff. Geometric, we multiply to get from number to number. Infinite. Yes, we are going to be adding an infinite number of numbers together today, and so that'll be fun. Our learning targets: I can find sums of infinite geometric series. Yeah, that's all. I'm just going to add together an infinite number of numbers. And I can use mathematical induction to prove statements. And so let's start out with infinite geometric series. We're going to add together an infinite number of numbers. And so if we think about our regular geometric series, where it's just a partial sum, the equation is the first term times 1 minus the ratio to the n over 1 minus the ratio. Now, not every infinite geometric series has a sum, because here there's a couple things that can happen. First of all, we need to take n as it's going towards infinity. It's getting really, 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 really big. And so, things can happen. Either r is bigger than 1, notice that's absolute value, so it doesn't matter positive, negative. It's bigger than 1, or the absolute value of r is less than 1. If it's bigger than 1, what happens when we take a number bigger than 1 and take it to really, really big powers? That number gets really, 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 really big, and it's called divergent, and it does not have a sum. And so sometimes we can't. For example, if r was 2, we have like 5, 10, 20, 40, 80. Those numbers are going to get bigger and bigger and bigger, and we're not going to be able to add them together. However, if r is less than 1, it's called convergent, and it does have a sum. The equation, if r is less than 1, let's say r is 1/2. What happens when we take 1/2 to a huge power? Let's see, 1/2, 1/4, 1/8, 1/16, 1/32, 1/64. That's getting closer and closer and closer to 0. So this is getting closer and closer to 0. So we end up with the sum is equal to the first term times 1 over 1 minus the ratio. And that's all. It's actually an easier equation than the one we were using the other day. And I know it might be, it's kind of weird to think that this infinite series of numbers actually has a sum. We can think of the paradox where you're trying to cross a room. I know I usually hear of it, the shy guy is trying to get to the girl to talk to the girl, and so he moves half the distance. And then he gets halfway further, and halfway further, and halfway further, and halfway further. And he never actually gets there, because there's always half the distance left. Well, there comes a point when he's going to be close enough, it's not going to matter. But it's overall, like when you add up infinitely, and after an infinite number of steps, he will get there. How far has he gone? He has crossed that one room. He has gone one room length, whatever length that happens to be. And so we can add up these infinite things to get a nice number. And by nice, I mean non-infinite number. It might be an integer. It might be a rational number. We don't know, but we can do it. So let's look at an example. Let's go 800 plus 200 plus 50 plus blah, dot, 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 dot. We only need two things here. We need the first term, and we need r. The first term is 800. It's right there, first. And then r, how do we get from 800 to 200? From 200 to 50? We divide by 4, or multiply by 1/4, or 0.25. In fact, when you put it into the equation, 1 minus 0.25 might be easier. And the first term, so we have 800 times 1 over 1 minus 0.25. We can subtract those to get 0.75. So we have 800 divided by 0.75. which is 3,200 thirds, or 1,066 and 2/3, or 0.6 repeating. And speaking of repeating decimals, that's part of the topic today. Why would that be part of our topic? Well, if we have a repeating decimal like 0.58, 0.58, 0.58, 0.58, or 0.58585858, we could rewrite that. That's 0.58 plus 0.0058 plus 0.00058 plus 0.00000058. So we just keep adding 2 zeros because we have 2 digits that are repeating. That's why it's 2 zeros. If we had 3 repeating digits, it would be 3 zeros each time. If there's only 1, we'd just be adding 1 zero each time. Well, when we're adding zeros, we're multiplying by a power of 10, or dividing by a power of 10. And specifically, 10 to the second, because there's 2 zeros. So we could write this as a sum. It's going to be the sum of the first term is 0.58. The common ratio, we have 1 over 100. And so we could rewrite it. The sum from k equals 1 to infinity of 0.58 times 1 over 100, or 0.01 times k to the negative 1. So that's our r, a1, k minus 1, not k to the negative 1, k minus 1. And so with that sum, and that's just what we did the other day, with the sum, though, we could plug this into the equation we just saw. 0.58 times 1 over 1 minus 0.01, and we could find this number. But we already have that number. So what else can we do with repeating decimals? We can write them as a fraction. How could we write them as a fraction? Well, let's give this number a name. We're going to call it a. Let's let a equal that number. Now, what would happen if I multiplied this by 10? Well, we just move the decimal one place. We get 5.858585. How about if I multiply it by 100? We move it 2 places, so we get 58.585858585858. Well, if I have 100a and I subtract a, 0.585858, or 58.58585858 minus 0.58585858, wouldn't those decimals cancel? So we get 100a minus a is 99a, and then 58.58 repeating minus 0.58 repeating is just 58. Then we can divide. A equals 58 over 99. And we could reduce from there if we can. This one's not going to reduce, though, so we don't have to worry about that. And that is how you can write a repeating decimal as a fraction, even if it's not one of the ones that you know. All right, we will come back to this topic in just a couple minutes, because that's what I want to leave you with. But first, mathematical induction. So mathematical induction is a way to prove statements. It's a fairly algebraic way of proving statements. It's not like a geometric proof, although it works with geometry, but it works better with algebraic equations, and it's a formula in and of itself. So given a statement, whatever statement that is, there are 3 steps. Step 1 is we have to prove it's true for the first term. Step 2, we assume it's true for the kth term, whatever k happens to be. And it is just the kth term. Like, we don't put a number into it. Step 2 is literally assume it's true for n equals k, and then we replace the n's with k's in the equation. And then step 3, assuming it's true for the kth term, we prove that it's true for the k plus first term, the next term. And so, let's look at an example here. We're going to use mathematical induction to prove that some of the first n even numbers, which would be 2 plus 4 plus 6 plus 8 plus blah blah blah, plus 2n equals n times n plus 1. So step 1, we have to prove it's true for the first term. The first term is 2 should equal, we need to plug 1's in because it's the first term. So does 2 equal 1 times 1 plus 1? Well, 1 plus 1 is 2 times 1, 2 equals 2. Yes, it works for the first term. Second, we have to assume it's true for the kth term. So we're just going to take this and change out the n's for k's. We're going to assume that's true. That is the second step. There's actually no work in the second step. The third step, assuming that this is true, we're going to prove it for the next number. So we're going to go, instead of 2k, we're going to go 2 times k plus 1. And then the n's become k plus 1's and k plus 1. So k plus 1 plus 1, that's just k plus 2. And then this 2 plus 4 plus 6 plus 2k, that's what we just assumed was true up here. So we're going to take this stuff and we're just going to plug in k times k plus 1 there. So we have k times k plus 1 plus the next term, 2 times k plus 1 equals k plus 1 times k plus 2, because those two ones add together. Hey, we have a k plus 1 over here in both of them. We could factor that out. When we factor that out, what's left? K plus 2. So we have k plus 1 times k plus 2 equals k plus 1 times k plus 2, and that is a true statement. Thus, this formula works by mathematical induction. Again, we prove the first step is true. We assume it's true for the natural number k, and then we add 1 to the term and show that it's true. This is probably the toughest piece in here, and it's one of the reasons why we're spending 2 days on this topic, just so that you have plenty of time to practice this. Alright, so for the next and for the very last topic, this is the last thing I'm going to teach you this year, officially at least. Last example. And we're going to repeat a decimal. We're going to write 0.9999999. That would be 0.9 repeating as a fraction. What would 0.9 repeating as a fraction be? Well, we have only one digit repeating, which means we only need to multiply by 10 to the first. So 10a is going to be 9.9999 repeating. Then we can subtract 10a minus a equals 9.9 repeating minus 0.9 repeating, which means that 9a equals 9, which means that a equals 1. Wait, that's not a fraction? Well, it is a fraction, but more importantly, what did we just show? We just showed that 0.9 repeating equals 1. Just letting that soak in for a second. 0.9 repeating equals 1. And that's it.